This is chapter 7. It's all about regression and follows on from correlation. So chapter 6 and 7 go together well because we use what we did in the last video in terms of the product moment correlation coefficient and the covariance. It brings in some of the C1 work as well because we're looking at y equals mx plus c, and we have to apply and interpret the regression equation. So we have to interpret that straight line, the line the best fit basically. Now you might want to also go to this YouTube video to get a quick idea of what regression is all about. So there's the link there if you want to cut and paste that or pop that into, make a note of it and go to that for a fuller explanation of regression. But I'm going to work through a few examples, and by the end of this booklet you should be able to do these 4 things. Identify the independent and dependent variables. Calculate the equation of the regression line in the form of y equals a plus bx. Now it's important, it does follow y equals mx plus c, but it's actually in quite a different order. The intercept comes first and b is the actual gradient. We're going to have a look at coding, and we'll also look at the meaning of interpolation and extrapolation when it comes to the graph of the straight line. I think that should be extrapolation. Okay, let's move on then. We have y equals ax plus b is the equation of the line of best fit and connects the 2 variables in a scatter diagram. So we know, just think about, compare this to y equals mx plus c, and all we've done is we've put it in a different order and we've said y is equal to c plus mx. So you can see on this one a is replaced c and b is replaced m. First example, just to give you a quick recap on what we've done on C1. For the line y equals 2x plus 3, write down the gradient and the intercept of the y-axis of the line. So hopefully straightforward for you. If we compare y equals 2x plus 3 to y equals mx plus c, then the gradient, which is m, is equal to 2, and the intercept is equal to 3. Could also be written as 0, 3. And a little sketch of the line, well, that should be very, very straightforward to you. Pencil and ruler, please. Let's get this, I can't use it on there. I think that's maybe just a bit too squint. So I will try and make it straighter. There we go. And so on. So label your axes, pop your origin in, and it's going to have a gradient of 2, an intercept of 3. So it cuts something like that. So that point there is 0, 3. And that point there is minus 3 over 2. And for every 1 you go along, you go 2 up. So that's your gradient. And that's important to think about the gradient in this way. So for every unit that we go to the right, how many units do we go up or down, depending on what the correlation is. Okay, example 3 then. 2 even, example 2. A company would like to predict the sales of their new shops, the sales of their new shops are going to be. The yearly sales of 9 of their existing shops are known, and the sizes of the population of the towns in which each shop is sited are found. The size of the towns, X, in thousands, and the sales, Y, in thousands of pounds, are given in the table. draw a scatter diagram for these data and draw by eye the line of best fit through these points. So again, can you use a pencil and a ruler, please? Apologies from me because I don't think I can do it on this package, this app. So I'm just going to do it fairly freehand. So we've got Y on here, and this is the town size. And we've got X on here, which are the sales. So we're not going to start at 0, we'll start at 10 for the sales and 40, so on. So we need to go up to 80, so 50, 60, 70, 80. And along the way we need to go to 70, so 20, 30, 40, 50, 70, 80. If you've got square paper, then that would be great. And I'll just emphasise again, in an exam situation, you probably wouldn't have to do it from scratch. You would just need to do plot a couple of points. It would say complete the scatter diagram for this. So if we put the first one on, T40, it's roughly about there. 26, 62, this is all very rough. 28 and 53, it's about there. 36 and 65. 48 and 72, 52 and 70, 54 and 73, 60 and 76, and 50 and 50. Okay, so you can see here, we're going to draw it by line. So if you've got a clear ruler, a 30 centimetre ruler, it makes it so much easier. Place your ruler on its edge and try and get more or less the same number of points either side of your line of best fit. I think it might look something like that. Now this one is a bit strange, and we'd probably call that an outlier, and we'd probably ignore it. So either the reading's gone wrong there or just an anomaly of some sort. So that should all be GCSE work for you, and what we need to be able to do, instead of drawing this line of best fit by eye, we're actually going to calculate. So we're going to calculate the equation for the line of best fit. So this is taking you up a step from GCSE, and we can actually accurately draw y equals a plus bx, which is the line of best fit. It's actually called the regression line, given a fancy name. Moving on to the next section, independent and dependent variables. The independent variable is also called the explanatory variable. Independent or explanatory, and it's the one that is set independently of the other variable and is plotted on the x-axis. The dependent or the response one, so the dependent or response variable, are one whose values are determined by the independent variable, and that usually goes on the y-axis. So in this example, let's see which one is the independent variable and which is the dependent variable. We have a company wants to predict sales of a new album by a pop group. They know the yearly sales of a number of existing albums by the same group and the number of stores that stock each album. So, the sales that's one variable, and the stores that stock the album is another variable. So we've just got to decide which one is dependent and which one is independent. So the sales, I would say that that is the dependent variable. So it would go on the y-axis because it depends on the number of stores that actually stock the album. And what would that look like if we were to quickly sketch that? On the y-axis, we'd have sales, because sales depend on the stores that have the albums for sale. So that's actually the stock that's available. So you need to know these new terms. It could be called independent or explanatory, and it could be called dependent or response variable. So that's the two new definitions. What I'd like you to do now is on exercise 7a, we've got two questions to do, 1 and 2. So looking at 7a, the first question, the number of operating theatres and the number of operations carried out per day. So which one depends on what is what we've got to ask ourselves. So if we look at the first one, I would say that that's the independent variable. So independent, because the number of operations does depend on how many operating theatres that you've got. So Y would be the dependent. A park ranger collects data on a number of species of bats in a particular area. So again, I would say that that's your X and that's your Y. Number of suitable habitats would be your independent, because the number of species depends on where they live or the suitable habitat. So this one is dependent. We're now going to look at the line of best fit, and it's also called the regression line. So that's the name that we give it at A level. And at this point it would be quite useful if you go back to the very first page, and there's a little video on there on YouTube about regression lines. So we can see here for each point on the scatter diagram you can express y in terms of x, where E is a vertical distance from the line of best fit. The line that minimises the sum of the squares of the residuals is called the least squares regression line, and that's what we base it on. So what we try to do is get the distance from the line as small as possible, and that's called the regression line of y on x. That's really important, that statement. The regression line of y on x would give us y equals a plus bx. If it was x on y, it would be x equals a plus by. So that it's important the way that you actually describe it. We've then got an equation, and as you can see we need to calculate covariances. And we also need the mean of y and the mean of x. And that's what chapter 6 was about, trying to find the covariances, and from that we can actually get our line. So in an exam situation, chapter 6 and 7, you'll find the question actually involves both of these topics together. And you'll be pleased to know that this equation here is given. So that full thing there is given in the formula booklet. So no need to actually memorise it. Right, we've got an example of it then. Example 4. The results from an experiment in which different masses were placed on a spring and the resulting length of the spring measured are shown below. And you might have come across this in physics before, and it's actually called Hooke's law. And you get the length of the spring is proportional to the mass that's added on it. So we're probably, if you think about the in real life situation, we are expecting a positive correlation, and so therefore a positive gradient. Okay, we want to go back to what we were doing in chapter 6, and we want to be able to calculate S subscript xx. And from that equation, remember it's the sum of all the x's squared minus the sum of the x's all squared all over n. And there, as I said before, you've actually been given all that information, so you don't have to work it out from first principles. It makes it a little bit more straightforward and quicker really for an exam. So we have 22,000 there minus 300 squared over 5. So that gives me an answer of 4,000. If we work out what Sxy is, that's the sum of x times y minus the sum of x times the sum of y all over n. So xy is equal to 18238. So I'm just getting these figures from the beginning of the question. And that's all divided by 5. So the final answer for that one is 922. So we've calculated Sxx and Sxy. Now why is it asked that? Because we need that to work out what b is. Because b is equal to Sxy divided by Sxx, which is 922 divided by 4,000. Now if you write the full display of your calculator and then if you round it, we always look for at least 3 significant figures. Now it doesn't feel exact enough to do that, or when we've written the equation of a straight line, it's usually just whole numbers or fractions at the very most, but in statistics we use figures of 3 significant figures, or numbers that are 3 significant figures. So what we do is we put A equals y bar minus b x bar, and they've been given to us as well, or we can calculate them. So we have A is equal to 57.72 minus 0.2305 times 60. Now if we look back at the question, we can see here that x bar is given to us and y bar was given to us. So that's where I've used it, and I didn't have to actually calculate it. More or less the information will be given to you. So to work out our value of A, it's equal to 43.89. So instead of drawing the line of best fit by I, we have now got a calculation of a plus bx. So y is equal to 43.89 plus 0.2305x, and that's what's called the regression line. So it's just given a fancy name now at A level, and it's just the line of best fit. So what I'd like you to do for this one is question exercise 7a, and it's question 3 onwards. The next part is about coding. Again, we use coding to make the numbers easier to work with or smaller. The coded regression line may not be the same as the actual regression line, and the linear change may affect the answer. So coding does actually affect the regression line. So what we need to do is change the variable and then simplify it and then decode it. So we'll do an example of this with example 5. 8 samples of carbon steel were produced with different percentages C of carbon in them. Each sample was heated in a furnace until it melted, and the temperature M in degrees Celsius at which it melted was recorded. And the results were coded such that X had that code and Y has that code. The coded results are shown in the table, so they've been given to us and we can work it out backwards really. So if we look at all the information that we've got, we've been given bits and pieces there. So you may use, and that's what it usually says in the question, so it saves you working them all out. So for part A then, we've got S, X, Y is the sum of X, Y multiplied together, and the sum of X's multiplied by the sum of Y's all over N. Substitute our numbers in, and we've got 478 minus 36 times the sum of all the y's is 144. So you have to work that part out, it's not been given to you, and altogether there are 8 pieces of data, and that works out to be minus 170. Right, if we now work out SXX, and again, why is it asking that? Because we need it for the regression line. We're going to work out what A and B are. So it's the sum of the x's squared minus sum of x's all squared all over n. So the sum of xx is equal to 204, that was given, minus 36 squared all over 8, and that's equal to 42. Right, part B, we're asked to find what the regression line is. So if we work out what B is, it's S, X, Y divided by S, X, X. So we pop our numbers in, and we get minus 170 divided by 42. So B is equal to minus 4.048. I've taken that to 3 significant figures again. We know what B is, so we can write the regression line, and our regression line takes the form of y equals, this is still part B, y equals it should be y bar equals A plus B x bar. So if we rearrange that around, we can find out what A is from y bar minus b times x bar. So A is equal to, well, y bar is simply 144 over 8, and B we worked out to be that was minus 4.048 times x bar, which is 36 over 8. So A works out to be 36.216. So work to 3 decimal places there. You want to make it as big as possible. It doesn't really, don't do the full display of the calculator is what I'm saying. So the regression line is y equals a plus bx. So that's y equals a, which is 36.216, plus b, which is actually minus 4.048 times x. So that's our regression line for part B. Part C says find the equation of the regression line of M on C. So we have to look at how we coded our data, or our x and y. And what we have here for part C, we want M on C regression line. And that means we want to write M equals our A plus BC, where these values are going to be slightly different because we've got coding going on. So your y was equal to M minus 700, and that was all over 5, and your x was equal to 10c. So if we go back to our original regression line, it was y equals 36 minus 0.216 minus 4.048x. If we now replace x and y and then rearrange the equation to make m the subject, then we should get it back to where we started when it was uncoded. So y gets substituted into this part and x gets substituted into that part there. So let's see what we get. We have y equals, I actually want to replace y, so m minus 700 over 5 is equal to 36.216 minus 4.048, and that's times x, which was 10c. Right, if we multiply everything by 5, simply because we've got a 5 here, we want to try and get rid of that, and that becomes m minus 700 is equal to 181.08 minus 202.4c. Keep the m on the left hand side because it's a regression line of m on c, so m is equal to 881.08 minus 202.4c. So that is how you would uncode it. So the coding was given at the beginning, these. So those there, that's the code for y, that's the code for x. And then when we get a regression line of y on x, then we just take our codes and we pop them in for y and for x. And then it's just a case of manipulating, rearranging equations. So what you should be able to do now is on exercise 7b, I would like you to do question 3, 5 and 6. So that's exercise 7b, and we're now moving on to applying and interpreting the regression line. So this was a bit like when we did scatter diagrams. It's all very well plotting the graph and saying that there's a positive or a negative correlation. We've got to try and put that in context now to actually see what it means given the variables that we've got. So the regression line can be used to estimate. That's a key word there, estimate. Because it doesn't go through every single point, it's just the best line that you can fit for the data that you've got. Now, interpolation, we've used that before when we've estimated mean and median from grouped continuous data. Interpolation has a little bit different meaning here because we've got to try and estimate values within this range. So this is important because it's within the range of the data. What I'm meaning there is the mass could get bigger, so it could go up to 120, 130, but we haven't actually measured that. Or the mass could go below and say do 10, or it could do 5 kilograms, but we haven't got data for that. So the only data that we can estimate with are really the what we've got in the table. For extrapolation then, you've got to be very careful, very, very careful, because for extrapolation you're actually extending your regression line. And once you do that, it does become unreliable. And why should that be? Because the values beyond the data that you've got may not follow that pattern. If you think about the mass and the spring there, the resulting length is shown in this table here in example 6, the spring has a certain elasticity. So if you started to put on 120, 130, there might come a point where you put too much weight on it and it stretches completely and will not go back to its original shape. So if we started drawing or extrapolating that line, we might find that we will get a length that the spring will actually extend to, but it might not be true. We can't rely on it. So what we've got to say to ourselves is view extrapolated values with caution. It may not be reliable. That's all we're saying about it. Let's look at the example then. Example 6. So it's the results again where we've got a spring and different masses are put on there. We've been given the regression line, and the regression line was found to be this one here. So we can actually use this now to work out our estimates for the value of y when we've got certain masses. Now if you look at 35 kilograms, that's actually within the data set that we've been given. So that is what's called interpolation. So all we need to do there then, so A part 1 is take the regression line, 43.89 plus 0.2305x, and we know that x is equal to 35, so we can work y out to be 43.89 plus 0.2305 multiplied by 35. And that will give us a value of y to be 71.55 centimetres. No, it won't. Absolute nonsense, because when I look at the table, that doesn't make sense at all. So it should actually be 51.96 centimetres. A bit of a wrong calculation going on there. So we can work the other way as well. So in part 2, we're asked to find out the value of y when the mass is 120. So y is equal to 48.89 43.89 plus 0.2305 multiplied by 120. So y from that this time is 71.55. That makes a bit more sense. So what can we say there? We can say that this, although it's not asked for, I want to put this in the example just for you to have for your notes. This may not be reliable, as this is outside our data set. So, i.e., extrapolation is unreliable. We now actually want to know what these two constants are. So 43.89, so that's the intercept on the y-axis. So if you think about it, on the x-axis is the mass that's added, so that's the independent variable, and the length of the spring is dependent on the mass that's added to it. So what we've got here is something, a regression line that looks something like that. So if we put that onto a graph, we can actually see that 43.89 is equal to the original length of the spring. Hope that makes sense there. Now the next constant that we have to have a look at is the gradient. And the gradient is definitely 0.2305. Again, it would help if we draw the graph and you can see what's going on, and I would recommend this every time. So what we've got is our mass on our x-axis, and on our y is the length. It started off at 43.89, and for every kilogram that you add, it actually extends by 0.2305 centimetres. So that's the reality, that's the gradient of the regression line, and what it means is 0.2305 is the gradient. It's not enough to just say it's the gradient, we've got to put that into real life context. So that means when 1 kilogram is added to the spring, it will extend or stretch by 0.2305 centimetres. And this is a typical exam question, because you work out your regression line, but then you've got to be able to put it into the real life context. You've got to explain what the variables are doing according to that equation. Right, we've got a couple more examples, the next one being example 7, and we've got a scientist working in agricultural research believes that there is a linear relationship between the amount of certain food supplement given to hens and the hardness of the shells of the eggs they lay. As an experiment, controlled quantities of the supplement were added to the hen's normal diet for a period of 2 weeks, and the hardness of the shells of the eggs laid at the end of this period was then measured on a scale from 1 to 10. And here are the results. So we want to find the regression line. Now we've been given this information, and it says you may use, so that means that they've done all the legwork there, as it were, all the number crunching, and we can use that for our regression line. So what we have here are their covariance again, and I think this should actually say H on F from the calculations that I'm going to do. Right, so let's work out what B is first of all, and that's our intercept. So SFH divided by SFF, and that would be 56.2 divided by 112. So when you work out each of these, do some number crunching, but that's what it comes down to. So that is actually equal to 0.5018, and it represents the hardness units per gram per day. And then A is equal to H bar minus BF bar, which is the mean is of H is 6.543 minus 0.5018 times 8. So that is equal to 2.5286 hardness units, whatever that may be. So when we work that out, we've got H on F, so H is the subject. H is equal to 2.53 plus 0.502F, and that is our regression line. If you need to stop the video and have a go at working out those just for a bit of practice, the covariance, and then just taking your time over working the regression line out as well, then that's fine. Right, that was part A. So it's H on F, because H is the subject, so it's H on F. So Y on X is Y equals mx plus C, that sort of thing. Right, interpret the values of A and B. What do they actually tell us? So for part B then, we've got A, and that actually tells us the shell strength when no supplement is given. And we'll draw the graph in a moment just to give you an idea of what that looks like. So looking at the regression line, looking at the graph, if we draw it, the y-axis is the hardness and the x-axis is the food supplement. So again, on your x-axis is your independent variable, and on your y-axis is your dependent variable. So if it's going to cut at that point there, and it's got a gradient, that's at 2.53, and that's when the supplement's actually equal to 0. So as the food supplement increases, we get the hardness actually increases as well. And then that means that B is the gradient. Now what does the gradient actually mean? Well, for every 1 gram, so we'll call that 1 gram of food supplement given, we get an increase in the shell hardness, so that part there is 0.502. So it's the rate of increase of hardness. So for every 1 gram of food supplement given, the shell hardness increases by 0.502. And we could also call that the rate of increase of hardness. So it's important that you can actually interpret this regression line. Let's look at part C then. Explain why you should not try to calculate the shell hardness for a food supplement of 20 grams per day. So if we look back at our table, 20 grams actually lies beyond our data. And remember, this is extrapolation. And we said extrapolation is not reliable. So we have to explain that. So in part C, 20 gram represents extrapolation. And it's important that you use that term of the data, i.e. 20 grams lies outside the given data set, therefore could be unreliable. And that's worth a little 1 mark at the end of a question. So if it's outside your data set. Right, this is the last example, example 8, and then we're finished regression as well, chapter 7. Example 8 then. A repair workshop finds it is having a problem with a pressure gauge it uses. It decides to have it checked by a specialist firm. The following data was obtained. It's saying that we can use this data, so that gives us a bit of a shortcut. And then on the first part, we're asked to find out SXY. So if we plug that into the equation that we know, so that would be 52.04. So that's the sum of XY minus the sum of X, the sum of Y, all over the number of pieces of data that we've got. So sum of X times Y is 52.04 minus the sum of the X's, which is 19.2, and that's times the sum of Y's, which is 18.86. And that's over how many pieces of data we've got, which is 8. Now that works out to be 6.776, and we've actually shown it, so we can do a little QED. We're now asked to calculate XX, so using the formulas as we have from before, it's 52.8 minus 19.2 times 19.2, because it's x squared, all over 8 pieces of data, and that gives us a value of 6.72. Right, part B then. Use linear regression to find the value of A and B, giving your answers to 1 decimal place. So read the question carefully, because most of the time you'll give it to, say, 3 significant figures, but they're asking for a degree of accuracy. So we're going to get this regression line of y on x. So we need to find out what b is, and b is equal to sxy over sxx, which is 6.776, and that's divided by 6.762. So it's 1.0083. Well, that should, I've made a mistake there, it should be divided by 6.72. Don't know where the 6 came in, just a copying error. And again, that put your full calculator display down there, that's great. Right, to work out what, so that's our B value. To work out what A is, it's equal to 18.86 divided by 8 minus 1.0083. Keep your calculator display on there. Multiply by 19.2 over 8. So that's your X bar and your Y bar. If you look back at your data, you'll be given X as 19.2. So that part there is your X bar and that part there is your Y bar. So if we work A out, pop that in your calculator and you get minus 0.0625. So our regression line is y equals minus 0.0625 plus 1.01x. Now if we look back at the question, it did ask for 1 decimal place. So really we want to write that as minus 1 plus 1.0x. So just be careful. But this is the usual form where you've got lots of decimal places. So I would make sure, read the question carefully so you know what degree of accuracy you're looking for. Right, the next bit that we want to do is part C. Draw a scatter diagram to represent these data and draw the regression line on your diagram. Squared paper might be useful for that. It's not asked so much to draw that in an exam situation because as you can see the accuracy that you need to draw to this and this is quite difficult with the graph paper that we've got. It's not got that accuracy. So I'll let you do that by yourself. And then the last part that we want to look at is the gauge shows a reading of 2 bar. Using the regression equation, work out what the correct reading would be. Right, first thing that we need to check then is 2 bar, and 2 bar would actually be about there, wouldn't it? So we're doing interpolation, so that's absolutely great. It's going to be fairly reliable. It's still going to be an estimate, but it's fairly reliable. So we'll use this equation for part C. And we get, I'm going to use the full, not the 1 decimal place, but I'm going to use 1.0083 and the rest times 2 minus 0.0625, and that's equal to 1.95 bar. So as you can see, the reading of the gauge was 2 bar, but using our regression line it should actually read 1.95, and that is quite reliable because we can see that the 2 bar is interpolation, is within our data set. Right, on exercise 7C then, the questions I am expecting you to do is question 7. Right, that's the absolute bare minimum, everybody, and the mixed exercise you can have a look at as well. But what I'll do is go through this with you in class on Friday, and as I said, we will do some regression equations, questions, exam questions, and correlation questions as well. The Stats 1 book is on the bookshelf in our classroom, and we can check the answers on that.